Yeah, I'll try to make it super short, so really don't worry about it. I want to start with an old and funny joke from the communist times. So there is a village in Soviet Russia, and there is a rumor in the village that in a week in the village club there will be a movie about love. And like everyone is super excited. They come at the time of date announced to the like club, and the guy from the like Communist Party or Komsomol is going on the scene as he's saying like everyone knows there will be a movie about love now, and there are many types of love, like a man to a woman to a man, woman to a woman, etc. But this movie will be about a very special kind of love. It is the love of Soviet people to the Communist Party. And therefore, I'm kind of talking about interpretability of deep learning, but I will start with a few stories that emphasize that it's pretty much impossible to understand what the hell is going on inside. And then maybe I will show a few things, like how to start picking a look at it. But I tested it on my students a few weeks ago, the last time I planned to come here. And the talk was much, much longer. And they started to fall asleep after more or less 1/3 of it. So I tried to divide it into a few parts. So this is part 1, and like, inshallah, if you like it, next time we will continue from part 2. So this one will be, I tried to make it as fun as possible because my students, like, they tend to fall asleep really often in the lectures. I tried to make it like so, mostly with copy-pasted fragments of code and like IPython notebooks that people smarter than me wrote. I tried to make it very easily reproducible. I'm not sure if I have access to all these netbooks because I'm accessing the presentation from another account. But all of it will be shared with all the participants. I think the organizers will help me with that. With that, let's start. So yeah, why do people need interpretable models? Generally, everything related to deep learning is historically treated like a black box. No one knows what is going on inside. And then from time to time, maybe like if you are reading this scientific popular literature, there will be, oh, there is a new way of totally like explainable machine learning, whatever architecture, and then people forget about it. And then in half a year, there is a new one. But like in practice, people like explainability in general. One of my stories will be about it. In addition, some of the industries require the models to be kind of debuggable. At least they like if you're working in insurance, they prefer things that they may they may see why a model gave this or that conclusion. And yeah, I will tell you 3 stories about things related to explainability. And the first one is about emergence. So the former head of Google search, Amit, he was a guy who was opposing introducing deep learning in ranking in Google search. He wrote the whole essay about it, that like everything needs to be explainable, and now they use deep learning in ordering the results. And he said that like if you cannot figure out why the thing is not working, then probably the system is not good enough for production using search, etc. At the same time, I've been working on a project called WebRef, and the goal of the project is figuring out what the page is about, determining the topics of the page, or determining the topical entities of a web query. So if you are entering the classical example, what is the age of Barack Obama? It knows, oh, the age is such a concept that we have like an arc in the knowledge graph, and Barack Obama is this guy, most likely it is the president of the US, like not Obama, the city in Japan or whatever, you know, stuff like this. And this system was started like long time ago as a system that was based on like pure statistic, everything was clean and nice, until probably, I don't know, I wasn't there, until probably the second week of the life of the system, when the first hand-tuned rule and hand-tuned coefficient was introduced. And since then, the system has become this like hairy ball of hand-picked numbers and rules. And really, like, no one could explain why the thing is working or why it fails in some cases. Debugging was a nightmare, etc. And therefore, the problem of deep learning not being explainable, in my humble opinion, isn't in like, oh, there is a neural network, etc., but it is the classical like emergent properties phenomenon. You have a lot of simple paths that are interacting with each other in a complex way, and the behavior emerges that is not explained by the behavior of each individual element. It is kind of like, you know, you have a human society, you talk to everyone, and they are normal human beings, but somehow at the football match, all of them become this, you know, rowdy crowd that goes, crashes the shops, and kills people with machetes in Krakow, you know, stuff like that. So this is emergence. So that was the first story. The second story is that if we want interpretability, people think that probably if something is interpretable, then we can predict its behavior. And in general, this is not true. Because if a model has the power to explain, it doesn't necessarily mean that the same model has the power to predict. And it happens at times that there is a model that lacks predictive power at all, and it is better at explaining things than the model that is able to predict. And with that, my second story is related. Once upon a time, and most of these stories are true, right? Some of them are not. Once upon a time, I've been working on a product that involved building recommender systems for the like end users, and it turned out like one of the UX experiments demonstrated that if, along with the item to recommend, you were showing the recommendation reason to the user, the chance that the user would interact with the item was like, it was a really dramatic increase, something like, I don't know, 20 or 30%, which is a lot of money. And then we tried working on the models that provide this explanation. So the models were generally based on the whole user profile, and I had access, like the model had access to all the items from the user's history. And in theory, the best way to explain would be the same way that was used to make the prediction. But it turned out that another model had to be built purely for explanation. And then it provided only a string with the explanation from the user. It was a totally different system from the one that provided the recommendation itself. And so it worked, and yeah, the users were happily clicking, buying stuff. So yeah, explanation doesn't equal prediction. And the third story is if you start debugging things, like you have a fancy machine learning system doing whatever, and something goes terribly wrong, right? Then at least from my previous experience, most likely it was the data that was used for the training that was screwed up rather than the model architecture itself. And like once upon a time, I just happened to be in the room where a like huge investment bank was defining their requirements for the new system to predict the risk of giving credit to the large institutional clients. And there were like all these things argued about. I was just sitting in the corner. And there was an item about explainability. Oh, we need to be able to debug. And not that I was like smart or anything. I was just out of discussion, and I was not interested in the outcome, and I felt like I can ask a random question. I asked guys, like in your data set, do you have at least one case of a large institutional client failing to repay the credit, and they said no. And then you know what happens if you are calculating like the interest rate. You can go infinitely low with this interest rate and still earn for years before like a black swan comes and eats you. Yeah, so mostly the problems are with data, not with models, right? So yeah, why really bother about explainability of the models then? And it is this part about the love of the Soviet people to the Communist Party. So the first thing is debugging. Yeah, sometimes things are going terribly wrong and you need to find the reason why in order to fix something, because like your system is down or whatever. Also, it is very important for building intuition, and usually you build intuition in order to be able to come up with better architectures, both better like performance-wise, quality-wise, and also maybe able to withstand the adversarial attacks if they ever happen. And finally, I think the reason that most of the people from outside, like hardcore machine learning engineers or whatever, will enjoy it is being able to build cool things. So, yeah, regarding the intuition, there is this tool called Deep Learning Playground, if I remember the name correctly. And it allows you to experiment with really, really basic, fully connected neural networks. If you never played with it, then do. You specify some simple data set, like in 2 dimensions, and you build a simple, fully connected neural network. So you specify the number of layers up to, I don't know, 5 or whatever. You specify the number of neurons, and then you may see it training, and I'll try to click. Oh, no internet. Okay, so I think we will survive without that. But yeah, you see on these connections the magnitude and also the sign of the weights that the network learns between the units, between the layers. And if you look at each particular unit, you see which shape it predicts for the inputs that it gets from the previous layer. So this is the basic way to visualize the internals, but it applies only to really, really simple networks, of course, because the modern ones are millions of units, you cannot squeeze it on the screen. But what's with like more fancy stuff? And it turns out that since if we want to build intuition about how the thing works, it is better to visualize, and the most visualizable networks are those for image processing, is convolutional neural networks. So just in order for you to like recollect maybe, if we have multi-layer neural networks, the like reasoning of people is that at each layer it learns some kind of abstractions, and then the way to transform one kind into another. This is like, it is close to reality maybe for some architectures, but it is totally artificial names, right? It is not that only edges are identified at layer 2. So in general, I think that in deep learning, you should approach the attempts of researchers to explain how the things function with a huge grain of salt. Like if you are into recurrent neural networks, and then in the paper you read that this is the forget gate and this is the whatever gate, then it is just the inspiration. No one really knows what is the real function of each individual gate. It is all created by trial and error, which makes it interesting. Yeah, so a network learns some abstractions with each layer. And let's hope we can visualize them somehow to understand how the thing works internally. In general, with CNNs, there are 2 approaches in order to understand the internal workings. One of them is to give the trained network an image and look at the activations. Or maybe afterwards, and I'm not showing this here. If you are interested, you may go to the examples for the book of on Keras by François Cholet, and they are on GitHub. I think I have some links at the end. But visualizing it works, it is not real fun. It is fun to try to backpropagate in the image to see, for example, if we identified a cat and a dog on the image, what parts of the image they come from. And this is called attribution. So yeah, this is going from the image to the network. But also, what if we take one neuron in the network and try to backpropagate to the image so that we maximize the output, the activation of this neuron. And yeah, this may be done. In the first case, this is for one neuron. In the second case, this is for one layer. No, not one layer, one channel in the CNN. Yeah, and this is called Fischer Visualization. And like this terminology is pretty much mixed up. People are using Fischer Visualization to denominate attribution sometimes. It doesn't really matter. But there are two ways, either to maximize the value of a neuron or to come from a picture and see what happens in the network because of this picture. So again, because of no internet, I will not click on the collab notebooks, which will make this talk even shorter and pizza even closer. But this is an example pretty much copy-pasted from Cholet's example, totally built with Keras. It allows you to see where the where the given class is coming from, right? Which part of the image. And this was, I think, for baby elephant, and it kind of identified the piece of baby elephant. Again, this approach cannot be really used for image segmentation or object detection or whatever, because like its results are really approximate. It just tells that this is probably the most characteristic part of it for the network. It doesn't try to figure out where the whole object is. And yeah, Fischer visualization. We take a neuron or we take a channel in the CNN. We try to maximize its value. And we backpropagate to the image itself, starting either from some random noise or starting with some image sometimes if we want to. And this gives us the thing that kind of excites a given neuron the most. At that, it's not only the one neuron that we may optimize for. In the first case, this is a single neuron. In the second case, this is the whole channel. Most of the illustrations here will be about the channel because they are the fanciest ones. And then, if you heard about Deep Dream, then we can maximize the activation of the whole layer. This is kind of simulating some kind of abnormal brain activity in a patient or something like that. And you can get some pretty fancy images of that. I wanted to start with this talk with like psychedelic video created with Deep Dream, but then I thought that maybe not. Maybe next time when the sponsors will provide drugs. But yeah, we may optimize for the class logics or class probability, and this is the distinction that one set of units is before the softmax, so the thing to determine which class dominates, and the other one is after. And usually it is more like fruitful to optimize for the logics because the easiest way to make the model predict a given class is to minimize the probability of all the other classes. So the side effect of it is an image from which you cannot conclude much. Also, there are other theories why it works worse. And yeah, there is a tool that allows you to do that. It's called Lucid. There is a tutorial on which I wanted to click and go through it, but I think if the slides are shared with you, you may do it all by yourself. It is made mostly by people from Google, but it is open source, and they invite people to contribute. And yeah, all these beautiful images are created with it. And yeah, then if we backpropagate to the image itself, then you might ask, why not just look for the examples in the data set that maximize the output of a given neuron? And there are a few good reasons for that. And the primary one is that each image contains multiple features, and you don't really know which of these features make the network tick and which of them are just correlated with the key ones. And like in the case of trying to detect the whatever, baseball balls, it really tries to detect the stripes. And this is obvious from the backpropagated image from the artificial one. But from the data set, it may not look like that. And the same stuff, like if you are trying to detect the roofs of historical buildings, etc., the things that it really looks for oftentimes is the sky. So you never know. But on the other hand, choosing the images in order to illustrate the examples, I think it is a good approach. Again, there are all the kinds of, if you try to backpropagate naively into the image itself, you'll see the high frequency noise on the picture that is dominating the picture in some cases. And there are different approaches to regularization. I will not go into details, I think, in order to fight it. And if you're using this lucid framework, the default values usually work well enough. And if not, then there is a link to the notebook where you may play and adjust all of them. Again, if we take one neuron and we want to maximize its activation, it is possible to take the same neuron and try to minimize its activation. So find the thing that suppresses the output the most. So if we have blue and things with sky and cloud and with straight lines, the thing that depresses this neuron the most is the thing that is green and purple, and it is all curves, no straight lines. But again, for each individual neuron, and I would really it is a shame that the internet is so sloppy here, but I would really encourage you to go through the examples and try to click on them. Again, if you backpropagate into the example, no one says that there is only one true whatever example of a dog. You may always try to infer several artificial pictures, and in order to do that, you impose one more limitation on what the model is looking for. It is the distance, however you define distance, between the examples it comes up with. And it is possible to try to activate two neurons at once. So this is a good example of one neuron activated by fluffy stuff and another one with a mosaic kind of stuff. And if we optimize for the maximum value of those two jointly, then there will be a mixture of these two. There are more interesting results with other things. And then it is almost the end of the talk, luckily. I inserted, so this is a deep dream image that I was able to generate. It is far from perfect, but it is with really simple code. From the image of Barbie doll taken for my daughter. And so this is how deep dream works. Also I have inserted a notebook with a really simple example of neural style transfer. You take a photo and you take a picture and you apply the style of the picture to the photo. In this case, this was some stuff from China or whatever, and the painting by Van Gogh. And this stuff you can really do in Google Colab, in these free IPython notebooks in the cloud in a matter of few minutes with these examples. Yeah, and I added some articles with additional reading. There is a group of people that is interested in explainability. They have a blog called distill.pub. They treat it as a replacement for scientific articles because it is much more interactive, etc. And it's worth going through them. There are beautiful examples, most shamelessly copy-pasted by me into this presentation. If you have any questions, please feel free to ask. Also, if you have any questions about, like, because I see that most of the attendees are young people, if you have any, if you'd like to talk about career building or stuff like this, then I'd like to be useful. Yeah, thank you all.